Hello, my name is Gerald. I'm a PhD student at the BU Material Robotics Lab. The title of my talk today is a soft robotic haptic feedback glove for colonoscopy procedures. The motivation behind the work is that a lot of minimally invasive surgeries, specifically colonoscopies, suffer from limited haptic feedback. The flexible nature of colonoscopes make it difficult to estimate the amount of force the surgeon is applying, especially when the colonoscope is looped within the colon and presses against the tissue as seen in the image on the right. Excessive application of force in such a scenario can result in severe adverse events such as bleeding or perforation. Haptic feedback could be beneficial in such a situation and could especially benefit novice endoscopists who are prone to applying excessive force. So an overview of the current solutions and literature. On the left image is a sensorized gripper that provides audiovisual feedback to the endoscopist in training. The image in the center is a sensor that uses elastic fabric for distal tip force sensing on the endoscope. And the image on the right is a VR colon simulator that provides haptic feedback as the trainees navigate through the virtual colon. But however, there seems to be a lack of a comprehensive system that provides both force sensing on the colonoscope and then provides direct haptic feedback to the endoscopist without sensory substitution. So we present a haptic feedback glove, which has modular actuators on the fingers, and that interfaces with a soft robotic sleeve. The soft robotic sleeve can detect force, and this results in proportional inflation of the pneumatic actuators in response to the force feedback. The glove itself is controlled by pulse width modulation, which produces vibration and inflation together to have a combined sensation of tactile and pneumatic feedback. So a bit about our prior work in soft sensing. This was published in the IEEE RAL journal. We designed a soft robotic sleeve with optical waveguides that can be mounted onto a colonoscope. And when there's deformation on this soft robotic sleeve, the optical waveguides show a decrease in light transmission, and this can be calibrated to detect the incident force. And when this incident force occurs and crosses a certain value, the soft robotic sleeve itself has pneumatic actuators that can inflate to redistribute and reduce the contact force, as you can see in the video on the right. So here's how the actuators are fabricated. We laser cut heat weldable fabric into these T-shaped patterns and sandwich those two T-shaped patterns of heat weldable fabric between Teflon and subject the laminated layers to a heat press at 150 degrees Celsius for 10 minutes. Then you have the completed actuators that you can see in the image on the right. So we validated our setup using a force calibration test. This was done to determine the relationship between incident force on the soft sleeve and then the inflation of the actuators in response to the incident force. So we had a instron with an indenter press on the soft robotic sleeve, as you can see in the inset image, and then the actuators inflated in response to the stimuli, and we recorded the pressure. And you can see that in the graph on the right. The actuators inflate proportionally to the applied force on the sleeve, and this happens once the incident force crosses a threshold of about 1 Newton. The threshold value is highly tunable and can be modified depending on the procedure. This is because peak forces in colonoscopies vary a lot between max forces ranging from 12 Newton to over 40 Newton. Our actuator achieves a max pressure of about 53 kilopascal at an incident force of 2.2 newtons, and it has a max pressure inflation time of 103 milliseconds, which is fairly rapid. We also subject our system to a force amplification test. This was to evaluate the force exerted by the inflating actuators due to the incident force on the soft robotic sleeve. And as you can see on the inset image on the right, we had a force input onto the sensor. This is processed via the control circuit and then causes inflation of the haptic glove. We block the actuator when it inflates using a load cell to measure the block force exerted. And you can see that on the graph on the right. The maximum force output of the actuator was about 9 times larger than the input force, and the actuators were able to exert force as the input forces increased beyond 0.75 Newton until about 2.2 Newtons. We also subject our haptic feedback glove to an in vitro Validation in a mock colonoscopy setting, as you can see in subfigure A, we used an artificial plastic colon, then had a surgeon navigate through it using a colonoscope with the soft robotic sleeve mounted on the colonoscope and the surgeon wearing the haptic feedback glove. You can see the data from that in figure B. And then we had the surgeon evaluate the glove using a NASA task load index, or TLX, which contains 6 subscores, including mental demand, physical demand, frustration, etc. A lower score on the TLX signifies a more efficient, easier workload with less discomfort. As you can see in the table, we tried navigation with haptic feedback and without haptic feedback, and then varied the sensitivity of haptic feedback. The trials which had haptic feedback had lower TLX scores than without haptic feedback. This essentially means that it was a more efficient workload and it was easier for the surgeon. The next steps would be to evaluate the device with surgeons of different skill levels to see the impact on haptic feedback on improving or easing the workload of the endoscopy. And haptic feedback could be particularly beneficial with novice surgeons who are prone to applying excessive forces and are not familiar with the intricacies of the procedure. And also, we want to spatially map force onto the actuators when the colonoscope rotates and then the orientation of the soft robotic sleeve changes. And we plan to do so using gyroscopic sensing. Lastly, I'd like to acknowledge my lab, the Material Robotics Lab, and my PI, Dr. Russo, and the National Institutes of Health for funding the study. Thank you.